Hey TJ Machine Learning Club. So today we're going to be lecturing on support vector machines. If you guys didn't already watch the previous lectures on decision trees and random forests, make sure you guys already do that because there's some concepts that were kind of introduced in those lectures that we kind of are building onto in today's lecture. Alright, well, let's get into it. So starting off with just a basic overview, SVMs are basically just supervised learning models, which are commonly used to separate different sorts of classes, help classify linearly separable data, or even perform regression at times. Although SVMs are most commonly used for classification, since the support vectors are kind of help us split the data and classify accordingly. And the reason these are called support vector machines are due to the support vectors, which are these sorts of problems are the data points nearest to the separating hyperplane, or kind of what we call the points of a data set that, if we remove them, would alter the position of the dividing hyperplane that kind of separates, two classes of data. And because of this, these support vectors can be considered the critical elements of a data set. I'll kind of get a little bit more into that because if you guys don't really have any background on SCMs, that might have been a little bit confusing. So with the basics, here we have, like on the right, just a basic linear classification problem where we have two classes of data and we're drawing a line to separate the data into its proper classes. So here there's multiple ways to separate this data into two classes. On this bottom right over here, we have these two dash lines along with this one kind of solid line here. So how are we supposed to pick the best one? Of course, if humans are just looking at this data, we obviously can kind of see that this solid line over here is clearly the best separator. But like we got to think about why, when we are looking at this data, do we say that? Well, it's because the margin kind of between this solid line and the nearest points on either side, these x's or the circles, is the largest possible. So kind of intuitively, how we think about it is the solid line is a better separator than the dashed line, and we could say that this happens because the solid separator line, or this decision boundary, is best because it's maximizing the distance from the nearest data points, or the margin. Because in an SVM, each point is treated as a vector, and thus these nearest data points, for example here and here, or here, these can be called support vectors because they're kind of the crucial data points that make our distinguishing lines like these. So if we want to maximize the margin, what we do is, since our goal is to use this decision boundary here to predict whether unclassified data points will where they would fall. For example, will a new data point, if I add a new data point right here, will this be a blue or yellow class? So since if I put a new line here, or a new data point here, since it's on the bottom side of this line, our SVM will predict that this new point is going to be part of the blue class. So this is kind of the goal of an SVM, to make some sort of separation where we can add new points and then use them to, or we can predict based on our kind of decision boundary. So if this decision boundary, however, is too close to either group, our model is going to perform poorly when given new points. For example, here, where this decision boundary is really close to this yellow X and also this kind of blue circle here. So if I added a new point, for example, right here or so, this line would kind of misclassify it as being a yellow X, when in reality, if there's a point that's right here, it should be a blue circle. By maximizing this margin over here, we minimize the potential error from generalizing. And what I mean by this margin is, for example, this line right here is the optimal hyperplane, but the kind of distance between these kind of dashed lines can be thought of as the maximum margin. And these dashed lines are normally going to be lines that are kind of on or connecting these different support vectors. So these two red squares and this little blue circle are kind of the support vectors of this situation here. And this hyperplane is the most optimal because this margin is the largest, and thus this would be the best way to split this data in half, or split the data between the red and blue. So when we have multiple dimensions, however, it gets a little bit more complicated because if we add more input features to an SVM, so instead of classifying between, or if we're adding more than just like the two features, the decision boundary will have to increase in dimension as well. So this is why the margins normally they're referred to as the positive and negative hyperplanes, because the dimension of a hyperplane is actually one less than the dimension of a feature space. For example, here we have a 2D kind of a 2D feature space here, and the hyperplane is one less than that, and thus is a 1D line. In this situation, we have a 3D hyperplane, or a 3D feature space, and thus our hyperplane is actually a 2D plane that goes between the two kind of clumps of points. So this is kind of just a little bit, if we need to have, if there's more than two dimensions, we'd still be able to separate it by using some sort of hyperplane. So moving on to the loss function. So there's lots of more complex math behind how we determine this loss function for a basic SVM. And if you guys go to the lecture on the website, you can actually go a little bit deeper into that. However, just because I know a lot of our audience is hasn't really taken like calculus or multivariable or more complex math, I wanted to keep this lecture a little bit more um, theoretical and just kind of talk about concepts, and thus I didn't really go into the deep math. But this 1/2 times the magnitude of the vector w squared is a loss function of a basic SVM, with the w being a vector normal to the hyperplanes, and it can be minimized using Lagrange multipliers. And again, if you guys want to go more into that, you guys can look at the lecture, or you guys can just search it up. So basically, what we're trying to do by minimizing this loss function is we're trying to maximize the margin of error. So if we get this 1/2 magnitude of w squared as low as possible, this margin that we discussed here will kind of uh, increase as much as possible, and that's kind of the goal. So this is kind of what a loss function is, and kind of machine learning is something you kind of want to maximize or minimize to get a better classifier. Okay, so moving on to soft margin classification. So kind of what we showed here with these kind of clumps of points were very easily separable by just one line or a plane, right? But in reality, we know that it's not going to be this easy just to separate points, um, like in these scenarios where every single blue point is on the left side and every yellow point is on the right side. In some scenarios, there will be no way to just draw a straight line that will, divide these points. For example, if I draw a line going through here, we will always at least misclassify one point. There's no way to draw a straight line that would kind of separate both of these classes correctly. And the problem with this is that our loss function would never be able to kind of minimize completely if there are some points that are always incorrect. So, to adjust for these cases when the data isn't as easily separable, but can almost be separated through a linear boundary. For example, here, I mean, it's not perfect, but we still would want to use some sort of linear boundary. What we do is we can just adjust our loss function by adding a new constraint C that has a cost for any data point that falls within the margin on the correct side of the separating plane, hyperplane, or on the wrong side of the hyperplane. So this is kind of the equation. You're adding C plus the sum of this kind of new penalty here. But what we can just, the simple way to think about it is the loss is now 1/2 times the magnitude of the normal vector squared plus the C, which is our new constraint, times the number of mistakes. So C here is a hyperparameter that controls the cost for each misclassified point. So we can change this, which means that the higher values of C mean that our model will be punished more for wrong points, while if we make our C a lower value, our model will be punished less for having more mistakes. So thus, if we have extremely high values of C, which means that we're making sure that there's barely going to be any mistakes, this could lead to overfitting. But on the other hand, if we had some extremely low values, this would create, or low values of C, which allow lots of mistakes, our models would not be very predictive, and thus, this machine learning problem goes, it's kind of essential to figure out what's that balance between the overfitting and the accuracy that we need to get with C. Also, if we think about it, with our previous equation with without the new constraint c, this is essentially the same thing as saying c equals infinity, because here we weren't allowing a single misclassified case or so. However, now we're basically kind of changing c and allowing us to kind of change the value of it. So now we can move on to nonlinear classification. So some data sets can't be linear separable or approximated by a linear decision boundary. So in these cases, using a soft margin SVM will not work because of course, we had some way to kind of linearly distinguish the data. However, for example, in this case on the top right here, if you guys can see, there's really no reason to use a linear separator here, and it's really inefficient. It would lead to pretty much a 50% accuracy, or pretty low accuracy. So since this soft margin SVM would be a really poor choice, we could work around this by using a new mapping function to project our data to a higher dimension, as was shown in this figure, where our data goes from 2D to 3D, and then we find the proper separating hyperplane, and then return it back to the original 2D dimension, and now we have this little circle here that kind of resembles the hyperplane that's separating the two classes. So now we have the blue and red properly separated by just kind of adding a new dimension. So here when we're projecting our 2D data to 3D space, this end result is like the circular decision boundary, and essentially what we're doing is just adding a new dimension z, which is x squared plus y squared. This is kind of one of the mapping functions that we could use. So kernels are functions that allow us to calculate a dot product of the higher dimensional points. So like we won't actually have to do any sorts of projections like done here. So in this way, they're kind of different sorts of functions where you calculate the dot product and it kind of makes it easier. Because as you can imagine, the projection function and the subsequent dot products done on the projected points are really computationally expensive. So to get around this, using this kernel trick is really convenient. Because for an SVM, we don't really care much about the projected points. We just care about the dot products. So some really popular kernel functions are the radial basis function kernel, or which is actually called the RBF kernel, or a Gaussian kernel. And these are different kernels you guys can actually experiment with when using your machine learning models or coding machine learning models. Okay, so now we'll move on to non-binary classification. So because all these problems here, we're talking about separating two classes here, red and blue, or the circles and the x's, or things like that. However, it gets a little bit more complicated once we deal with multiple classes. So, I mean, SVMs are mainly designed for binary data just due to the way they work, since they're kind of just drawing some sort of distinction in a hyperspace in a plane between two classes. Although they can be extended to multiple classes by making kind of um, some slight changes to how we're using the SVM. So there's two major methods, the one versus rest or OVR method, where we're separating one class at a time from the rest of the data. So what this means is if we have four classes, we would treat this as a series of binary classification problems. So we would have one SVM that separates class 1 from class 2, 3, and 4, and another SVM that separates class 2 from classes 1, 3, and 4, and so forth. So kind of we're going to create the same amount of models as we have classes. So this is kind of pretty computationally simple, but it kind of oversimplifies our problem a little bit since we're separating just this one class from every other class in the space. The other method is one versus one, or OVO, where we make a model to separate every class from every other combination of classes. So we're basically creating n times n minus 1 over 2 models from n classes. So what this kind of means, because it's a little bit complicated to think about, is if I have four classes, so class 1, 2, 3, and 4, we'd have to create SVMs that separate classes 1 and 2, 1 and 3, 1 and 4, 2 and 3, 2 and 4, and 3 and 4. We basically have to separate every combination of classes. So I'm going to make this a little bit simpler since this is just kind of an overview. So in OVR, of course, we're splitting the multi-class dataset into separate binary classification problems. So what this means is the binary classifier is trained on each binary classification problem, and the predictions are made using the model that is most confident. So here's kind of an easier example that makes it a little bit more intuitive. So here we have different red, blue, and green marbles. So first we'd kind of make one sort of classification algorithm that would separate the red from the blue and green marbles. Then we would have another classification algorithm that would separate blue from red and green, and then the same thing with green from red and blue. So what we're doing here is we're kind of creating algorithms to three separate algorithms that when we given a new point, we could determine based on the results from all three algorithms whether this new point will be a red, green, or blue point. So there's multiple ways to do this. Either you can use argmax, so like in I don't know if you guys have used NumPy, you know the np.argmax method, which means that if these three classification algorithms are returning a probability from 0 to 1 or so of the of that class being a red, green, or blue, it'll take the average or like the max of the three probabilities and kind of return that. That's what argmax is doing. Another option is if all the algorithms return a output. So say the first algorithm will return an output of red, and the second two will return a blue, and this one will return a not green or so, right? Or say or if the let me rethink about this. So what it would do is if these three algorithms are returning different points, but for example, majority of them are returning red, red, and red, or I guess in these two cases it would be not blue, not green, then it would take the majority vote, which would be red, and then say that the overall SVM would give a output of red. So this approach was requiring that either each model predicts a membership probability or probability like score, which is where we'd use argmax. And yeah. Then we have the one versus one situation. So like the one versus rest, we're kind of splitting this multi-class classification problem into smaller binary classification problems. But the kind of major difference is that we're splitting it into one binary dataset for each class. But in the 1v1 approach, we're kind of splitting it into one dataset for each class versus every other class. So before in one versus rest, if we have three classes, we'd have three binary classification problems, one for red, one for blue, one for green. But with one versus one, we could have a lot more binary classification algorithms than we actually do have classes. So the formula for calculating the number of binary datasets is number of classes times number of classes minus 1 over 2, or n times n minus 1 over 2. The kind of downside of this approach is that it could require a lot more models and classes, as I was discussing, and this could be an issue for huge datasets, or if we had, say, 20 classes, because now we'd have to use 20 times 20 minus 1 over 2. Um, we'd have to use um, that many algorithms, and thus in that type of scenario, it would be a lot more computationally efficient to just use a one versus rest method. But here's an example of one versus one. So if we have here a blue, yellow, red, and green marbles, now instead of just making four separate algorithms, we'd have to use red versus blue, red versus green, red versus yellow, blue versus green, blue versus yellow, and green versus yellow, all six different scenarios of combinations of the two colors and determine the most votes or the argmax of the probabilities coming from each algorithm together to determine the most likely color of a new output or a new input into the model. Um, so as we can see that for these four classes, this is giving us the expected value of six problems that we're saying, because 4 times 4 minus 1 over 2 equals 6, and so forth. So moving on to kind of finishing off the lecture of just the pros and cons. Now that we got like a better understanding of what really SVMs are, so some of the pros, I guess that we could have pretty much figured out are that SVMs can have a pretty high accuracy since we're kind of making a large distinction between multiple classes. They can work well on smaller data sets that are cleaner. And what we mean by cleaner is that they um, have a lot, like each point, there won't be as many outliers. And also the SVMs can be more efficient since they use just a subset of training points. However, the disadvantages are that the SVMs are not really suited to the large datasets as the training times can be high. As we were saying that if we're using lots of classes, we'd have to use lots more algorithms than if we were to use a different machine learning approach. Additionally, they're really like less effective when we have lots of noisier datasets with some overlapping classes. Because like in these images that we were looking at, the classes were very distinguished. For example, when we're back here, the classes were very distinguished between blue and orange or so. And there we didn't really have any scenarios where it's just where there's lots of outliers or so. But if there are lots of outliers and it's kind of hard to distinguish between the two classes with just some sort of line or hyperplane, the SVM accuracy would be really low. So it kind of depends on how noisy the data set is like whether or not you should use an SVM. Just for the general uses of SVMs, they're normally used for things like text classification, since you can kind of assign different text to different categories. Or it can be used to detect spam or sentiment analysis because it could detect spam by kind of sorting your inbox between spam or normal emails just based on how the SPM works is kind of the separation between spam or not spam. And it can work for sentiment analysis, which is kind of also another growing field, which is about using like text or so to determine the kind of emotions behind the language used in the text. SVMs can also be used for image recognition, and one of the very popular machine learning datasets out there, the MNIST dataset, can be used actually on that dataset. So I encourage you guys to also think about maybe how you could apply SVM to the MNIST dataset. But yeah, that's all we have for today. I hope you guys learned something a little bit more about SVMs, and yeah, we'll see you for our next lecture.